Recent advancements in aerial robotics have enabled the use of multirotors for payload transportation. However, it is challenging for classical methods to reliably model a quadrotor carrying a cable-slung load. On the other hand, purely data-driven learning methods do not comply by design with the physical constraints of the system. In this work, we propose the use of a physics-informed neural network to learn an end-to-end model of the system. To guarantee the cohesiveness between multiple predicted states, we train the network with a physical model of the system derived from first principles, and we use slack variables to allow for a small mismatch between expected and predicted values. The proposed neural network has an LSTM encoder-decoder architecture with an attention mechanism. The network receives a temporal history of M-system states and control inputs and recursively generates predictions of the system state in the following n-time steps. To train the model, a loss function given by 4 separate terms is considered. L-fit is used to fit the observed data to the model, while L-physics embeds physical data to the model. L-projection forces a unit norm to the quaternion. L-slack allows for a small mismatch between the physical model and network predictions. To acquire real-world data, several experiments were performed in a mocap arena with a quadrotor carrying a slung load. The drone was commanded to perform various flight maneuvers to excite different modes of the system. Here, we show the predictions of the state of the system for a single sequence of the test set. The time series predicted by the network are depicted in dashed lines over the expected values in solid lines. The time series predicted by the dynamics model are depicted in dotted lines. For comparison, the vertical dashed lines denote the prediction horizon of 25 time steps used during training. In this figure, we provide a comparison between the evolution of the mean average and standard deviation of the prediction error of the proposed model and a physical model state predictor, derived from first principles, evaluated on the test set. From these results, it is possible to conclude the neural network outperforms the classical model and its standard deviation increases at a slower rate. To evaluate the impact of imposing physical constraints on the loss function during training, we show the evolution of the mean average and standard deviation of the prediction error of the proposed model over a baseline model trained without physics. From these results, we confirm that enforcing physical constraints on the model reduces the mean prediction error over the prediction horizon. Having the drone performed an ellipsoid trajectory while varying its altitude, in solid lines we present the predicted trajectories given by the neural network for the drone position and the payload, while the dotted line is the ground truth.